thank the directors and the engineers of this Energy Management Cell for this unique opportunity to present this webinar. We appreciate the proactivity and agility to to accept this and to accept our invitation. We appreciate the proactivity and the interest in boosting productivity and for the enthusiasm in enhancing productivity through improving power quality, energy efficiency, reliability of electrical networks in the state. As we grapple with this deadly and mysterious virus, COVID-19, which has affected every aspect of our life globally, from personal life to livelihood, to business to governments, from the weakest to the mightiest. The key lies in adapting and evolving rapidly to the new norm. Periods of crisis is not new to humans. Each time it struck, humans with their indomitable spirit and resilience have adopted, evolved, and overcome many a times. It can't be different this time. Let us resolve to reinvent and rise from the ashes of Harmonics again to a glorious future. Country's advancement is driven by innovation, political leadership, engineering excellence, and entrepreneurship. As engineers, we have a sacred duty to perform, to reinvent and innovate like the Americans do, improve styling and designing like the Europeans, boost efficiency like the Japanese, achieve new levels of engineering like the Germans, attain the precision level of the Swiss, and emulate the Chinese in scale of manufacturing. We need to combine all these attributes if we need to reach new global levels of productivity and competitiveness. Let us begin by focusing on power quality because this is basic, electrical efficiency and reliability, because this I feel is basic to achieving our goals. With this, I will dive deep into the subject. So guys, we are special. We have been in this power electronic business for past 30 years, and we are now specialized in this power quality and harmonic mitigation. So this is all the we've been working for this for past 10 years in Tamil Nadu, and so our experience and expertise in power electronics and power have given us this edge and finding new solutions for not only just solutions, simple, cost-effective solutions for mitigating harmonics. So I will go through this subject. I'll be focusing more on harmonics and power quality. Power quality is a general term, but harmonics is a much more complex subject. So I will go deep into that subject only. So our agenda is harmonic. It affects the myth about power factor because that's a very critical subject about power factor. Because in a new environment, power factor, due to the harmonics and pollution, power factor will become difficult to maintain. And prevention and mitigation techniques and support the IE standard 519/2014, which is the latest standard for harmonic mitigation. And then optimize the advanced mitigation techniques, and then a few case studies. You have all these power quality is all encompassing term for power disturbances. You have various power disturbances, and everybody is aware of it. Use blowing, nuisance, equipment failure, malfunctioning, equipment overheating, system losses and line losses, damage to sensitivity, penalty imposed by utilities. So these are all the different power PQ issues that you have. But transient sag, swell, undervoltage, momentary interruption, long-term interruption, steady-state voltage distortion, which is harmonics, and then the flicker and the noise. But the harmonics is the subject which is cycle by cycle you have a problem. The other disturbances may occur infrequently. So, and that is something which can be solved quite easily. But when it comes to harmonics, it's a difficult subject. That's why we are focusing on that subject. So you have this in the power quality issues, transformer issues such as noise, extra heat, premature failure, panel, neutral wiring, and other distribution equipment running hot, printed circuit failures, drive, PLCs, industrial PCs, extra. Breaker overheating and drive shutdown, premature motor failures, contactors, stopping or poor network communications, high utility bills, poor power factor, and low system capacity. This types of there are two types of loads. One is the linear load. You can see that blue is the voltage waveform and the red is the current waveform. They are perfectly in sync and they are continuous and proportional. The current waveform is the red waveform, which is the current waveform, is proportional to the voltage waveform. So it is like, it starts at 0 degree and then peaks at 90 degree and then collapses to 0 degree at 180 degree. So this is the continuous periodic wave. This is an ideal waveform that any load would require. But this you can find it only in a resistive load. So that is the linear load. Now the subject of harmonics arises only because of non-linear load. Because due to automation, robotics, and other power electronic equipment to improve efficiency. So typically the drive it improves the efficiency, but the flip side of it is the current drawn by it is discontinuous, and hence harmonics is the waveform gets distorted, and that anything which is other than sinusoidal waveform is called a distortion. So it introduces distortion into the electrical system, and this causes a lot of problems, which I will go into it in my subsequent presentation. So this is a pure sinusoidal waveform, and it is the ideal supply net, ideal supply. But in reality, it is not there because of these non-linear loads. When a repetitive and predictable non-zero voltage or current distortion exists, this means the supply contains harmonic distortion. So this is a typical distortion that you see in red in three-phase drives. So what are harmonics? So typically the fundamental waveform is 50 Hz. You see that blue waveform, blue color waveform, green color waveform, which is a sine wave. Okay, that is 50 Hz sine wave. But you will also see the third harmonic, which is in blue, which is 150 Hz. So you will find three waveforms in one cycle. So that is the third harmonic. Then you have the fifth harmonic, that is 250 Hz. It's written wrong, of course. It is actually fifth harmonic. So that is fifth harmonic. So like that, you have the seventh harmonic, which is about 350 Hz, and then ninth is about 450 Hz. So it goes on continuously like that. So these harmonics get superimposed on the sine wave, and the resultant voltage waveform will be in the red. That is the ultimate waveform, which is not even voltage gets distorted because of the current waveform. When they get distorted, the voltage also gets distorted. So you will see this. This is a graph which shows the 150 Hz about 23% and 250 Hz is about 11%. This is calculated, in percentage. It's 100 into the square root of 23 squared by 100 plus 11 squared divided by 100 will give you the. It goes on like this. If there are other harmonics, you go on adding those harmonics, and that will be the total harmonic distortion. So this is the subject that we'll be dealing with it. So this in a single phase switch mode power supply. Normally in computers and other instruments and other digital equipment, all have power supply. And most power supplies are switch mode power supply. And they are designed with the diodes and the capacitors, smoothing capacitors and all that. So what happens is when the power is given, the capacitor is charged only when it reaches the peak. So that is why you find when the current is drawing at the peak, the voltage gets flattened. So this is the voltage and the current waveform from SMKS. Normally, the distortion in the current distortion sometimes reaches level of 60 to 80%, depending on the filtering circuit the SMPS is installed along with your computer. It supplies power to all the disk drives and the other processors and all that. They have multiple outputs from this SMPS. So this SMPS they cause a lot of distortion in the power supply, in the electrical network. And imagine when there are 100, 200 computers, the type of distortion it causes. So it can be an havoc. So that's another thing. Then we also have a variable frequency batch. We call it DFT, we call it DSP, or whatever it is. We have the 6 diodes, okay, and with the same thing, filter capacitor, the output, the input distortion will be the voltage and current waveform will be this type. The blue is the voltage waveform and the red is the current waveform. This is what you see in the output of you. If you use the scope, you will find the output in, like this. On the power analyzer or in the scope, you'll find this type of input distortion in drives. So normally they'll be to the extent of 40%, 60%, 70%, 80%. It depends on the quality of the drive, the design. So these are the two major loads that I projected. So why we have issues with harmonics is because there's a different sequences. So if the fundamental is positive, the second harmonic is negative, and the third is zero sequence, and then again fourth is positive, and fifth is negative, and then it goes on continuously. So you have positive, negative sequence, and zero sequence. Each have different amplitude and phase angles. So this is a real issue when dealing with harmonics because they are at different phase angles and different magnitude and amplitude. So the issues of harmonics takes a serious turn. So the direction of you just see the direction of it is normally each phase is separated by a 120-degree phase shift. So normally they cancel out at the neutral and it is zero. But when it comes to neutral current, you see them adding up. You see them adding up to the neutral. So suppose there are 10 amps of neutral current, third harmonic current. What happens is each phase has 10 amps, 10 amps. There is about 30 amps of this third harmonic current close to the neutral, and they sum up at the neutral or add to the neutral. They are additive to the neutral. So this is the issue with the third harmonic and unbalanced flow. When there's unbalance also, we put the unbalanced portion of it close to the neutral current and then add up to the neutral. So that is the slide showing that. So the third harmonic is again a serious issue. So its magnitude is high and it can be very harmful also. So these are different sources of harmonics. Anything which is AC DC conversion, any AC DC or DC to AC conversion. When you say AC to DC, that is converter, and DC to AC is inverter. So UPS, welding machines, induction furnaces, computers, a lot of all this generate these harmonics. And this is now all loads are there's no load without these types of loads. So the effects of harmonics is it's important to understand the effects of harmonics. Harmonics have deleterious effects on electrical equipment. They can be itemized as follows: capacitor bank failure because of reactive power overload, resonance, and harmonic amplification. Normally, capacitor bank acts like a harmonic sink, and they react with the network. So that is the big issue. Excessive losses, peaking harmonic tops and oscillations in induction and synchronous emissions that may give rise to torsional stresses. So what happens is fifth harmonics in motors driven by drive, there's a fifth harmonic component which is a negative sequencer. So the magnetic flux tends to be on the reverse. So what happens is the positive and negative causes a torsional vibration, and you have bearing failures, insulation failures, and the premature failure of the motor itself. An increase in negative sequence current loading of synchronous generators endangering the rotor circuit and windings. The same strip harmonic causes all these problems. Uh, Generation of harmonic fluxes and increase in flux density in transformers. So the transformers get saturated because of harmonics and eddy current peaking and consequently derating. So which results in many using K-rated transformers to absorb these heat. But they don't mitigate harmonics, but it causes it does it withstands the thermal stress. That's called K-rating transformers. Low voltages and excessive currents in power system resulting from resonance. I'll come to the subject of resonance later. So these are all the ill effects of harmonics. So, rating occurs due to additional eddy current seeking, skin effect, and possible dielectric breakdown. So this happens through the cables. Inductive interference with telecommunication systems. This happens sometimes when telecommunication cables run closer to the electrical cables. And signal interference and relay malfunction, particularly in solid state and microprocessor control systems. Interference with triple control and power line carrier systems, causing disoperation of the system with accomplished remote switching, load control and metering. So anything digital is a serious problem. Unstable operation of firing circuits based on zero voltage processing, section and latching. Sometimes there's a voltage drop to zero in few nanoseconds or microseconds. And this zero voltage is sensed and it causes this operation. And interference with large motor controllers on power plant excitation systems. So these are all the ill effects of harmonics. So now to understand the CHT, there's two things. Mostly all plants use generator and the grid supply. Generators, most industries have generators. So there is a difference when you have harmonics. The voltage distortion in the grid, you notice that it doesn't get distorted much. The voltage at a CHT of 43.98, the voltage distortion is 0.6. That is because of the strength of the grid. It is a very strong source, and it has got a very low impedance. So voltage does not get distorted. So in the grid, voltage doesn't get distorted because it's a big source and it's a very strong source. It's a very stiff source. So voltage does not. But the same thing, the harmonics in the generator for lower capacity. What happens is, it being a weak source and with a high impedance, the voltage distortion is very high, 12.37%. So this is so the current distortion, as it flows through the various impedances, it distorts the voltage, current voltage, and this voltage is fed to the other equipment. So the voltage distortion is a serious problem when there is a current distortion. So again, to emphasize the point that when you connect a 75 HP drive to grid supply, which is a very strong source with low impedance, the voltage does not get distorted. Can you see the blue? It does not get distorted. So the current, which is in the red, is distorted. Voltage is not getting distorted. But at the same time, if this from the grid, the 75 HP drive is connected to a grid. The next slide. Yeah. Generator. Grid. Yeah. Generator. So the same thing, if you connect it to a generator supply, you see the voltage also getting distorted. So the voltage distortion also depends on the impedance value or XR ratio of the transformer. So with high XR ratio, the distortion will be less. But if it is low, then the distortion will be more. Similarly, in generator, the distortion could be more, voltage distortion can be more. So normally you will have to overrate your generator by say 2x or 3x depending on the level of performance. So I think it is important that to know the effects of harmonics on generator. The effects of harmonic voltages and harmonic currents are significantly more pronounced on generator. This is because the source impedance being 3 to 4 times that of a utility transformer. So that is important. Source impedance being 3 to 4 times that of a utility transformer. So normally that is why you have to overrate the generator. The major impact is rise in temperature in stator and rotor winding due to increase in iron losses and copper losses. Consumption of 1 liter diesel emits 2.5 to 3.5 kg of CO2, so environmentally unfriendly also. Light loading of generator causes operating inefficiency, so your operation cost of generator also goes up. So fuel energy consumption increases for every unit of energy delivered. So the unit consumption of energy also goes up substantially if you have harmonics. So generator automatic voltage regulator and excitation controls can be sensitive to voltage distortion that is created in supplying non-linear load. So when harmonics rich environment, the generator can have serious problem with the AVR also. So operation and it can flip. So these issues are being faced by many industries. So these are some basic formulas or equations about the PhD, PDI. So to calculate RMS, normally the fundamental current is calculated. For PhD, the distortion is not calculated. But the true RMS is basic fundamental into the square root of 1 plus PhD square. Because the Ohm's law applies for every harmonic. So as the Ohm's law applies for 50 Hz, the Ohm's law applies for third harmonic, the Ohm's law applies for fifth harmonic, similarly for other harmonics. And plus the skin effect and all this rising when you have harmonics. So the true power factor is, there are two power factor. When you say true power factor, it means two things. One is PS power factor, which is the displacement power factor. This normally you'll find it in inductive loads. And purely inductive load and passive load, it will be just displacement power factor. So, but because the introduction of automation and power electronics, the distortion is introduced. So you have power factor, distorted power factor also. So the formula is displacement power factor into distortion power factor. So actual power divided by apparent power into 1 divided by square root of 1 plus PhD square. So this is the calculation for calculating the true power factor. So sometimes when you have distorted power distortion, the power factor will be capacitor patterns do not really work at all. I'll come to that subject later. So the voltage THP and THPI is calculated this way. So from the second harmonic to the nth harmonic, you add the square root of that divided by the fundamental voltage. Similarly, the current, the calculation is done in the same way for calculating THPI. So this is the THPI, and then you have total demand distortion. So demand distortion is divided by the average demand. Average, the maximum demand current is the average, say, of 12 months is taken, and then they average it out, and this is called total demand distortion. So there's a difference between THPI and TDD. I'll come to that a little later. So some important things. Voltage distortion is a function of system impedance and current harmonics, and simple Ohm's law applies. VH is equal to fundamental the harmonic current into the impedance of the harmonic. So it could be third harmonic, fifth harmonic, whatever it is. That is how that Ohm's law applies to in each harmonic. The Ohm's law applies. The most dominant harmonics in industry are third, fifth, and seventh. Seventh and 13th in smaller quantities. Mitigating third, fifth, and seventh will improve power quality substantially. So this is the fact. If there are many industries they have done power quality study, and most of the major harmonics are third, fifth, and seventh. Once you tackle these three harmonics, you will solve the problem of voltage distortion and current distortion. And mitigating these harmonics leads to good power quality, efficiency, reliability, resilience. So not only that, your operating costs, your capital costs, all can come down to bring down your harmonics level. So every myth about power factor, there are various myths about this power factor when it comes to harmonic load. So there's a third dimension added to power factor when there are non-linear loads. So as I told you earlier, displacement into distortion is the true power factor. So if you see the first diagram, you will see that when there's a simple linear load, say an inductive load, simple insulation to adding a capacitor, as much as required for the reactive energy, will improve the power factor. So this is how it is calculated. So kVA of it is equal to square root of kilowatt square plus kVAr square. So this is the current that you have to draw from the transformer to support your loads. So this reactive energy has to be added. That is why it is called kVA. It's not kilowatt. So kVA is the current that is the total of the square root of kilowatt square plus kVAr square. But when it comes to non-linear load, there's a third dimension added to this thing. So you have another kVAr square, which is the harmonic kVAr. So kVA is equal to kilowatt square plus kVAr square due to displacement and plus kVAr square, which is the distorted reactive energy. So all reactive energy are not usable; they are just wasted, and they circulate between the load and the source. So each time they keep reversing forward, reversing. So each time you keep losing energy, this reactive energy. That's where it heats up the cables and all that, and the transformers. In the case of non-linear, the harmonic constants they produce no useful work and be called as reactive power. This distorted current adds a dimension to the power triangle and also increases the complexity of the electrical network as they interact with the impedance of the network and pull down the power factor. So it pulls down the power factor. When you have the third dimension, just adding capacitor will not solve the problem. It will not solve the problem. You have to mitigate harmonics to improve power factor. The true power factor now becomes a combination of displacement power factor caused by the inductive load and the distorted power factor caused by non-linear loads. Normally, THD or 40% have a power factor of 0.85 to 0.9. Normally, in price, the power factor is normally good. However, the power factor may still be low due to distortion power factors in the case of SMPS and drives. In SMPS and drives, the power factor is normally 0.6 or 0.7. It is not because of displacement power factor, but it is largely due to distortion power factor. Once you improve the distortion or decrease the distortion level, the power factor improves automatically. So the best way to improve power factor is by mitigating harmonics, preferably closer to harmonic producing loads. When harmonics is mitigated, power factor improves dramatically. So that is a very key important statement. When harmonics is mitigated, power factor improves dramatically. So normally people try to solve it by installing some active filter. I'll tell you why that's not the ideal way of ideal or the good or a good electrical factor to do that. I'll come to that subject a little later. So this you have three issues, 3 points you have to remember. What's the difference between resistance, reactance, and impedance? So resistance is a force that tends to resist the flow of electric current. In the case of a DC current, we say it is resistance. Perhaps the best news of all is that you are working with DC direct current. Resistance is the only thing you need to concern yourself. When you have a DC current, you don't have these issues of harmonics because there is no time variation. The slightly more complicated concept of reactance and it only exists in the world of AC. So when it comes to alternating current, you have only when you have these issues of harmonics and phase angles and all that. So reactance, we have to. This is the important thing that we need to understand what reactance is. So when we in an inductor and capacitor, we the resistance, whatever the electrical resistance we call them reactants, whether it's an inductor or a capacitor. So in electric and electronic systems, reactance actually offers only reactive competence. And it offers opposition of change in current. This is important. It offers opposition to change in current in a circuit, and it is frequency dependent. So it's a function of frequency. If frequency changes, reactance changes. So this is very important. If frequency changes, reactance changes. So reactance is similar to electric resistance, but it differs in several aspects. Reactance denoted is in a circuit or system stored, and there are stored devices that store energy and release energy as the current and voltage fluctuate with each AC cycle. So each time the cycle, there is a 50-hertz cycle. Each time there's a positive negative cycle. It keeps changing and keeps storing and releasing energy. So the formula, the equation is for XL is 2 pi FL. And if you see the graph with the y-axis, x-axis, and the y-axis, you see reactance and frequency. So in an inductive load, as the frequency increases, the reactance of the inductor increases. So the inductor has a higher impedance or resistance to higher frequency. This is the opposite in a capacitor. In a capacitor, the reciprocal of inductor. So XC, the capacitor reactance is 1 divided by 2 pi FC. So you will see this graph. So as the frequency increases, the resistance or the reactance to capacitor to reach a higher frequency becomes very low or infinite at one stage, and it becomes open when it is the frequency is low. So this principle is used basically for tuning or mitigating harmonics. This technique by manipulating inductance and capacitance or intelligently using a mix of this inductance and capacitance, we try to mitigate harmonics using a broadband filter or tuned filter. We use this technique here because when capacitance and reactance intersect, at some point when XL is equal to, so I'll come to impedance. Okay. Relationship. So this is the important relationship of inductance and capacitance. So you will see at some point at a particular frequency, when XL at a particular frequency, say it's assuming fifth harmonic, and a particular at that point, if XL is equal to XC, they resonate at that frequency. When they resonate at that, this is called the resonance. When you have an inductance of the system and the capacitor, when they interact, the frequencies interact with the network and they cause the resonance. So this is a serious problem in network where it is rich in harmonics. You have this problem. So it will be capacitive when XC is more than XL, it will be capacitive. But when XL, the inductive is more than capacitive, it becomes inductive. So this is how we manipulate and we try to create low impedance path for the harmonics. So it's got a dual effect. So one adverse effect of resonance, is this problem. See, when you have an inductor, a transformer with this inductance, a capacitor, and when XL is equal to XC, so XL is 0.78 ohms and 0.78 ohms. There's a frequency of a particular when it interacts with the harmonics, you can see this non-linear node. They introduce harmonics. This harmonics tends to flow to the capacitor. When they flow to the capacitor, they interact with the frequencies that they interact with the capacitor, generate new frequencies, and then they amplify that particular harmonic signal. And you can see the amplification of harmonics in this stage. So this is a serious problem when it is an inductive load, capacitance can solve the problem of power factor. But when you have a non-linear load, capacitor does not act like a capacitor. It acts like a harmonic thing and then interacts and amplifies the signal. So this is a serious problem. So this one shows the linear load and the capacitor bank and the non-linear load and how it flows back to and how non-linear load causes problems in supply and how harmonics flow to the network. So this is a resonance effect is there in a lot of installations because due care is not taken about the harmonics. So in that, to solve this, they use detuned or anti-resonant filters in series with the capacitor. So this detuned reactor acts as a high impedance to harmonic current to avoid resonance condition. So what happens is, and if you say if it is there is a fifth harmonic or something, you will have a 7% filter, which is about 189 hertz, and 189 hertz is away from 250 hertz. So they act as a detuned filter. They act like a blocking. They block the harmonics into the capacitor. In that way, you stop the interaction of this of the frequencies of the network frequency and the capacitor, and the amplifying the signal. It prevents that. So it is called basically a detuned reactor. So this detuned depends on the harmonic. If it is a third harmonic, normally they use a 14% reactor, which is about 139 hertz. If it is seventh harmonic, and they use the fifth 210 hertz, and then if it's fifth, they use that 189 hertz. So depending on the harmonic.
Anish, sorry to interrupt. Your voice is breaking somewhere. I think it is better you can switch off the camera, then we'll get better bandwidth.
Okay.
Yeah, you can. There is one the bottom right. There is one tab. You can click on that.
Yeah.
Next to the okay.
Cut it off.
Okay.
Is it okay now?
Okay. Yes, it is okay. So there was some missing in your voice.
Okay. Sometimes.
Okay.
Okay. So normally, when in most cases they use a detuned filter or anti-resonant filter along with your capacitor band to ensure that this amplification and magnification of the signals will occur. So it depends on what harmonic is dominant in the network. Suppose if say third harmonic, you normally use this 139 hertz reactor. We also call it 14% impedance transformer. So this blocks the third harmonic and to flowing to the capacitor, and it prevents the resonant. Similarly, in the fifth and seventh harmonics, it is dominant. Use a different type of reactor to filter to block. Basically, these are not harmonic filters. The myth, the myth is that sometimes some people believe that this will mitigate the harmonics. It will just not mitigate the harmonics. It just blocks the harmonics, prevents the resonance. Whatever harmonics is there in the system will remain. So only it will stop amplification or magnification of the harmonics. That's all. So this myth, I'm trying to show that myth. So, but
what does this percentage indicate? What is the percentage?
Percentage is the impedance of the inductor. Reactors are basically inductors. So when you have say 14%, the winding is more. So the magnetic flux induced will be more. So it is tuned to 139. When they interact, when this filter, when the detuned reactor and the capacitor will generate a different frequency, 139 hertz, away from the 150 hertz. So what happens is it does block the third harmonic. Similarly, if you have say fifth harmonics, the 189 hertz is away from the 250 hertz. So when it is away, it forms a high impedance path for that frequency. So it is basically a 7% impedance. So the winding will be little lesser than the 14%. Higher the percentage of impedance, more the winding and more the magnetic.
Okay, yeah. So if I want to block seventh harmonic, so what percentage should I choose? Should I go for 14% or 7%?
Normally, what they do is normally they use 7%, but you can use 5.6. You can use normally 5.6 7. But normally, everybody uses 7th because it is in between the 5th and the 7th. Or normally, I don't know. Somehow they use the 7th one.
My doubt is like 7. The harmonic is 7 times 50 hertz. So 7 times 50 hertz is around what?
No.
250, right?
350 hertz.
350 hertz.
It's
Yes,
350 hertz. But sometimes normally everybody uses 7%. Somehow, they don't use this 5.6. I don't find the reason. But there are these three ranges of manufacturers do manufacture these.
Yeah, that's what we have seen 5, 7, and 14. Even L&T also making. We have used it in some projects.
Yes,
So
yes.
the problem is that we don't know how to choose it. We thought that 7% means up to 7th harmonics it will block, and 14 for the higher. It is not like that.
It is not like that. So if you have third harmonic, you can use the 14%. 14%
Oh, it
is
is a rule.
expensive.
Okay, fine. Okay.
14% is expensive, so they go for 7% only. Because normally third harmonic.
Okay.
If
Okay, so 14% means by up to 139 hertz, these two will be in the resonance.
Yes. If it is away from 150 hertz, so 139 hertz, so it does block the third harmonic. But
the resonance means resistance will be low, right? At that time, it will block or it will pass?
It will have a high reactance to third harmonic.
Okay.
It is a blocking. When you say 14% impedance, it means that the inductor is wound more. The windings are more, so magnetic fluxes also increases in the inductor. So it becomes a high impedance path for that particular frequency which is generated in the network. So it's a blocking.
That impedance will decrease. Right? The reactance is coming to zero during suppose 140 hertz is the harmonic frequency. So
we
that
don't
time
we don't have 140 hertz. Normally 150 hertz.
150. Okay. Yeah, 150 hertz means that time this 139 hertz if I am placing means it will not block, right?
It will block. That's what I'm saying. 14%. That's why it will block. It forms a high impedance, but it is not away from the thing. So sometimes these filters may not be suitable also. If there are multiple harmonics and higher magnitude, then these harmonics can heat up and it can burn. It can burn up also sometimes. So if there are the harmonics is not very high, these filters are okay. But otherwise, if there is high rich harmonics, say about 20%, 20%, it may not be an ideal filter. So you'll have to resort to some other method or technique.
Okay, thank you.
So the ideal method we would, from my experience and expertise, we would say that filtering these harmonics closer to non-linear nodes. So suppose you have say a data center or something in your plant. To isolate that, and you had some filters and reduce the harmonics there, then it becomes very simple. Rather than doing some active filter activity panel and allowing this harmonic currents to flow inside the plant and then filtering it in the transformer. I mean, they are closer to the transformer is not an ideal method. The ideal thing is non-linear node. Sometimes when you filter these harmonics and harmonics are lesser than say 7 to 8%, then you may not need this inductor, this reactors also. You may not need. But there's no harm adding reactors. Only thing they may consume some power and electrical efficiency may suffer a little. So that issue will be there. So it is a trade-off whether you require reactors or not. It depends on the situation. You have to take a call, and depending on the level of harmonics. The ideal way is filtering it closer to this. So the important thing about this, the power factor degrades in spite of APFC network with substantial harmonic load. So when there's high harmonic load, the active power factor does not really help at all. It in fact can worsen because of resonance. Capacitor banks acts like harmonic sinks and interact with the natural frequency of the network in the presence of harmonics. They amplify harmonic signals and cause dangerous high voltages and current. If the voltages and current, can suppose if the fifth harmonic is resonating at the fifth harmonic, and if the fifth harmonic is normally say 10 amps, it can be 30 amps also. The voltages also can spike, and the capacitors can fail. So Q2 filters do not mitigate harmonics. They block harmonics and starting with the capacitor. They are basically, the right term would be real ideal term is anti-resonance. To improve power factor in harmonic-rich electrical bus, mitigating harmonics is a wide technique closer to notes will mitigate harmonics and improve power factor. So when you mitigate harmonics, you improve power factor also. So that's a very key important point. So to improve reliability of your electrical network, there's always a two way of doing it. One is prevention, and sometimes even despite preventive measures, you may not be able to mitigate harmonics. You will have to employ mitigation techniques. Prevention is better than cure, and preventing harmonics or mitigating harmonics closer to nodes would be the ideal and good electrical factor. This is not practiced in many places. I've seen it myself. So prevention of harmonics by proper planning. So you can keep the sensitive nodes away from the harmonic producing nodes, called non-linear nodes. So you can do it that way, or you can group the disturbing nodes. Group them separately. The disturbing nodes and sensitive nodes, because disturbing nodes closer to sensitive nodes would be a real issue, real problem. So keeping it away from the sensitive node is very important. And then separating the sources by with different transformers and separating them, so that even flipping a non-linear node becomes simpler. Once you mitigate harmonic closer to non-linear node, it will not affect the power factor and all that. So this little planning can be done when designing it. So there are other techniques of mitigating harmonics. So one thing is reduction. We call it reduction because correctly sized inductance normally installed along with harmonic producing loads. We normally typically the device all comes with reactors or so. So the problem is they come with 3% and 5% impedance, but you can't have higher impedance because voltage can drop. If voltage drops, the drives will trip. So you'll have to size them properly. You can use only 3% or maximum 5%. If you use the 5%, the shifting is better. So it does reduce harmonic, 20 to 30%, but they do not mitigate it totally. And they can reduce the peak currents also. So that's all reactor or stroke can do. But there's another technique called diversion, which is tune the passive filter to create a low impedance path for that particular harmonics and divert it. And then we have something called advanced universal passive harmonic filter, which I will come to that later. But the technique is diversion. In universal passive harmonic, besides diversion, we use other techniques also, like mutual inductance and all that. Phase shifting, mutual inductance, all that we use in a universal filter. That's why it is much more effective filter than the tuned passive filter. Tuned passive filter, you have other issues. When there are other harmonics, it can interact. When the source impedance and the load impedance changes, again, it can change. When capacitor efficiency comes down, again, the tune doesn't work properly. So there are a lot of issues with tuned passive filters. They are really, I would say, outdated now. Then you have phase multiplication and phase shifting. So, in a typical two drives, 2-6-pulse drive, if you have two phase shifted outputs of a transformer, say 0 degree and 30 degree, you shift it to 12 pulse, you convert it to 12 pulse, and then you eliminate 5th and 7th. You do not eliminate, you mitigate harmonics of 5th and 7th. But 11th and 13th will be there when it becomes a 12 pulse. Similarly, 15 degree, 3 outputs, 15 0, 15 3 output transformers, then you can convert it in 18 pulse. Similarly, at 24 hours, you can go on doing it. So normally this 12, 18, 24 is sorted. When you have multiple drives of the same capacity, you can use this type of transformer, 12 output, 3 output transformer. And you have the cancellation, which is the active harmonic filter. I will tell you about this active harmonic filter, what is the issues with it. So the active filter, the method is called cancellation. In phase shifting also some cancellation is a technique. In phase shift also there is a cancellation of harmonics. So normally, you have in a, typically in a drive, you'll see find when the group is saying, you can have up to 90 to 120%. Some to drive the PC jokes, so it is only about 35 to 45%. Some use passive filters, reduce it to 15%. Some use hybrid filter, active, passive, and all that, and reduce it to minimum 3 to 5%. So different techniques are employed. There's a cost always involved when it becomes you have to reduce further, the complexity increases. So now you have this 519, the latest standard is 2014, which is adopted globally for mitigating hormones. So the, the idea is that if the PCC or the bus voltage, it is less, you can have more harmonics is tolerated. So voltage harmonics can be 5% and the current harmonic can be 8%. But if the grid is improved, grid is higher, you can have only 1% individual harmonics and 1.5% current distortion. So as the capacity increases, they are not allowed higher harmonics because higher thing is distributed to other industries also. This is a current limit for individual harmonics. What you can have, it depends on your short circuit rating of your transformer. The short circuit rating is ISC divided by IL. You will, if it is less than 20, you can have a demand total demand distortion of 5%. But if it is very high, say more than 1,000, you can have a distortion of 20%. So higher ISCIL, you are permitted higher distortion. So this is available everywhere. I think I need not spend more time on this. I will go through this. So this is an important thing that you have to understand. The PCC, the point of common coupling. So the point of common coupling is the point where it is there from the substation, it is distributed to the other plant, and the measurement also is done at that point in the industry. So, so this is called a point of. This is where the TDD is calculated. So this TDD, TST and TDD difference you need to know. So as if the harmonic current is at 20%, you see that the TDD and the TST is almost the same. But as the load increases 100%, the harmonics remain almost the same. But TDD becomes very high. So at lower harmonics, the TDD is very high, but at more loads, the TDD will be low. So this is the basic thing. And TDD is calculated at the point of common coupling, whereas TST is calculated at load side, basically. So TST measurement is the local, and measurement is cycle by cycle. But TDD measurement is at measurement. See, I think some writing is wrong, but the idea is it is a cycle by cycle measurement, DST at load end basically, or anywhere in between. But the TDD measurement is done at PCC. See, the philosophy is very simple: that you are not supposed to pollute your neighbor's network. Okay? You can have as much harmonics inside your plant, no issue, but the utility will measure the harmonics at the PCC, and that is called TDD. So you have the freedom, you can swing your arms, but your freedom ends when the other man's no freedom. So that's again philosophy. So you should not export your harmonics to other. So for compliance, now I move to the subject of advanced customized mitigation techniques. So what is the implement? little revolutionary in terms of things because these filters are not available. You can search the cell and you will not find one filter that will match the performance of these filters. So that's why I call it advanced optimized mitigation technique. So we call it waveform terminator, and we have waveform triplen eliminator. When you say triplen, it's the third harmonic, third, 9, 15. All these are triplen harmonics. So then we have the waveforms advanced HMT, which is harmonic mitigation transform. Then we have the sine wave filter. Sine wave filter is not actually a reduction in harmonics, but to protect the motor and improve its performance. So this, I was talking about active filter being using a technique called cancellation. So they have they use digital signal processor, software algorithms, and all that. What they do is that they have a fast-acting IGBT. What normally it does is it senses the harmonic generated in the network, and then it generates equal and opposite pulse, which is equal to the harmonic generated in the network, and they inject that into the system. When the cancellation happens this way. So it is a complex electronic circuit involving microprocessors, DSPs, and IGBTs, which is IGBTs are powerful electronic equipment, and they are prone to failure. Depending on heat and dust, all these do matter on the performance of the active filter. That is why it is expensive. And reliability is always a problem because electronics, pretty totally electronics. And you can see that. You will see that the harmonics generated here, and then you see the reverse harmonics generated by the agent, and then you eliminate the other harmonics. So this is how this active filter does its job of cancelling harmonics. But normally they are very expensive. So the total harmonics is measured at say PCC, and normally this thing is installed at MB panel. So harmonics, it does mitigate harmonic closer to the MB panel and the transformer. But the harmonic inside the plant is not mitigated. They still remain inside the plant, and it will have these harmonics will flow to the other nodes, and the adverse effects or the ill effects of the harmonics will continue to be there inside the plant. So that is why this active filter should be used as a last resort when you are not able to mitigate harmonic using other techniques. I think this technique can be employed. But because there is no other options, all industries are using this active harmonic filter because they didn't have any other filter that could do the same work more efficiently or perform better. So the problem about it, they're expensive. They introduces higher frequency harmonics. So you may have the CMI issues also with this thing because the power analyzer measures up to 50 harmonic only. Above that, they don't measure. You have to use the spectrum analyzer. So it does introduce some high frequency harmonics, which can interact with your electrical network and cause other issues. So they are not totally good power conditions as such. So they are susceptible to background voltage changes. So the if there is higher distortion, it may not be effective. Then complexity requires startup and regular service by manufacturers. So it needs regular service and maintenance. So the cost of maintenance goes up. Generally, significant levels of ground leakage current, which can cause inadvertent ground fault trips and sensitive equipment failure. So and that can be a common mode noise which can cause disturbance in electronic systems. The voltage, the earth neutral voltage can go up and it can cause other issues. So normally they are installed along with, and you have to use the detuned power factor panels along with the factor. So that adds up to your cost. The cost of ownership is very high. Besides the capital cost of buying it, the ownership of the maintenance cost and service and all that can be very expensive. If the failure of a PCB can be quite expensive, and it takes time. Normally, it has to be a trained service engineer to repair it. So that's the issue for industry. They can't can't afford failure. If one active filter fails, the entire plant comes to a grounding halt. I come to this thing called Terminator. This advanced, we are calling it universal advanced harmonic filter, because this filter will, these are the problems with the drive. You see the front end, you see the 6 diodes. So they generate fifth and seventh harmonics and other harmonics to a limited extent. You can see the system. All these harmonics are distributed by the GFP. Without choke, you'll have this effect. The harmonic magnitude of the fifth will be very high, and to lesser extent seventh, and similarly 11th, 13th, and all that. And the output. So if you see the output of the inverter, AC inverter, it's a square pulse, prime-weighted pulseless modulated waveform. So square pulse, not AC. It's an approximation of sine wave, but nevertheless they have the switching, because of the switching, IGBT switching. You have the square pulse waveform, which is given to the motor, and that is where the other filtering comes in. I will come to that subject, but these are the issues with variable drives, and in some rectifiers you have the same problem. So this is the working principle of the terminator or the universal passive harmonic filter. It consists of multiple windings on a common core. So one single structure, with 3-leg structure, we will have multiple windings. I tell you why we have multiple. It works on a mutual coupling between the winding, helps to improve the harmonic mitigation performance. So what happens is there are multiple windings. So each has got a magnetic pulse waveform flux. So each magnetic flux is in a different direction. So what happens? They mitigate the harmonics. To stop the upstream flow of harmonics also. There is a winding also which will stop any other harmonics interfering with this filter. So any upstream harmonics also, we designed it in such a way below the fourth harmonic, so no other harmonics enters this filter. So dominant frequency will be diverted through a specially designed reactor. So besides that, using mutual inductance and phase shifting to mitigate harmonics, they use a tuned type of filter also. It's a broadband, basically a broadband filter, which will filter a wide spectrum of harmonics. So dominant frequency will be diverted to a special designed reactor winding, which helps to mitigate harmonics. 5th, 7th, 11th, 13th, and 15th. I will explain the thing in my next detailed working of it. So these are 3 winding. I'm just giving a single line diagram. So now normally there will be about 9 windings in one structure. I'm just giving the single line diagram. Okay. So this you have a non-linear load which can be a drive or something. You will have harmonic currents flowing, and this inductor L2 will limit some of the harmonics, say 7th harmonics or something like that. It will limit the 7th harmonic. It may allow other harmonics, but when it comes to L1 harmonic, it will filter anything. It will pass anything up below fifth harmonics, but it will try to stop the harmonics above the 5th and the above. So what happens is the residual harmonics that circulate here. The residual harmonic which circulates in a small quantities. Okay, we use a tuned circuit. So this capacitor and this inductor LC are tuned. You create a low impedance path by creating inductor and capacitor by designing it in such a way that XL is equal to XC, and so the impedance is almost 0. So what happens is the harmonic currents tend to flow through this and to the ground. So you have a complete filtering. And this L2, there's another work. This L2, this is winding is done on the reverse. So reverse polarity. Why we do it? When you have a magnetic flux in a forward direction and a magnetic flux on the reverse the voltage drop we will minimize the voltage drop. It cancels and does not allow voltage drop. Normally, when you have too much of inductance in series, voltage drops. That is the principle of inductor. But that principle is defeated by winding it in a different way to ensure that voltage doesn't drop. So you don't cause any voltage drop, but you cause high impedance for high frequencies or different harmonic orders. Plus, you have a diversion technique employed. You have an inductor and a capacitor. Now the special thing about this capacitor is we use a very small capacitor, maybe just 15% of the total requirement. Suppose the non-linear, the area requirement is say, 100 kVAR or something. We use only 15% capacitor because most of the harmonics is mitigated here. So we need just for only the residual. We are having a filter only for the residual harmonics. So the power factor also improves to almost above 9.5, very surely above 9.5. It could be 9.8 depending on the size of the capacitor and the load. The power factor also improves. So all you reduce harmonics, all the harmonics, right from it can be even designed as such, but normally drives only have fifth harmonic. So we design it from fifth to even the 100th harmonic. It can filter all the harmonics, and it will comply to IEEE 519 2018 2014, which is below 8% THC. Now this filter the performance will be equal to an active filter without the disadvantage of maintenance cost and all involved and high cost involved with active filters. So this preferably is better to be installed closer to loads, closer to drive. Along with the drive, it combines perfectly well. It improves protects the motor, it protects the drive, it protects the motor, and minimizes harmonics. Everything it does. So it's an excellent filter, very unique and very revolutionary. So all the harmonics, you're addressing all the harmonics, to even the 100th harmonic, or even say 400th harmonic also. So the key advantage is it allows the use of significantly small capacitor bank. As I told you, in other tuned filters, the capacitor rating will be very high. So if if the load is constant, there's no issue. But if the load falls down, there can be overcapacity. And when you have overcapacitance, you have ringing. When you have overcapacitance, then you can have resonance and then ringing and all that. So it can complicate the entire thing. So that disadvantage is removed with this type of universal filter because it is 15% only. So no voltage boost, no reactive power flow at no load. There's no voltage boost or no voltage drop also. Voltage also doesn't drop with it. So it is compatible with generator. Sometimes when there's overcapacitance, generator can be an issue. In this, you don't have a problem. So the harmonics treated as 5th, 7th, 11th, 13th, almost all the harmonics. There's no harmonics. So it filters all the harmonics. When it meets the IEEE 519 2015 standard. And waveforms terminators protects against system resonance. So the terminator protects against system resonance. So you will not have resonance even at low loads. You will not have resonance. And it improves reliability and higher efficiency. So the reliability is very high because it's purely magnetic. Magnetics is designed properly and temperature is taken care of. Even temperature, you can have over temperature, cut off facility and ensure that it doesn't fail at all. In case the temperature is high, it trips automatically. But if you rate them correctly, you will not have an issue with any for another say lifetime also. Except the capacitor, which has got about 1.5 lakh hours or 2 lakh heavy duty capacitors you can use. It can last you about 5 years, depending on your usage. So it is a very reliable, rugged, durable filter. is a diagram to show how these filters can be installed along with one single VFC motor or with multiple VFCs and motors. Suppose you have many VFCs in one panel, you can either have a one common filter price to the total capacity, adding the current rating of all the motors and VFCs. So we have installed filters for lifts in a building in Chennai. They had about 7 lifts, and there was a constant problem, failures and all that because of high harmonic levels. Besides the harmonic generated by lift, right, there was air conditioning plant HP receiver drive, which was adding up to the problem of this harmonic, high harmonic drive and repeated failure of lift. Lift is a very dangerous thing, when it stops, there are problems. So they installed this, we installed this filters there. So the harmonic level was as much as 107% in those drives maximum. And the current is varying, in fact, it can be from, just a few 1 ampere to, maximum 12 amperes. It's a variable load. So the filtering also becomes a little difficult. But nevertheless, they reduce substantially, more than 90%. And so it has improved the reliability of working, and we have reduced the harmonic filtering. So another thing, for the furnace load, furnace load, is a arc furnace. These arc furnaces, the current, the voltage, everything, and there can be a variation, a lot of variation in furnaces, especially when melting or melting those metals, or the current can vary a lot. So this was the thing which we installed, and there were 220 amps. The current harmonics was 27.7, the voltage harmonics was 3.4, and the fifth harmonics was almost 23%, and seventh harmonics was, you can see the variation also in the harmonic levels. So this is the problem. And then after we installed this thing, we found that the current harmonics came down to 7.6, 7.5, 7.9, which is within the IE limit, much below the IE limit. And you can also see the current and capacity come down also. The waveform also, the voltage waveform and the current waveform has improved substantially. The power factor also, you notice that it improved from 0.88 to 0.97. So this filter is a very effective filter, even when it comes to very demanding station like furnace, or the variation in current and power factor is very wide and wide also. This is a certificate we have received from that the case we installed for the 350 kVA multi furnace, and for complying with it. So I will briefly tell you about this active and the advantage and the disadvantage of active cutter. The active cutter is a very effective filter, no doubt about it. It produces harmonic current to 5% at PCC, also making good power factors in the system. Partial load performance is very good, also on partial loads also. Can be replicated to existing system and can be used with multiple non-linear loads. Large size, cost, and the complexity of the disadvantage of it is a large size, installation is complex. You'll have to install CPs and all that, big voltage, provide air conditioning. Sometimes if it is dusty, you'll have to keep the base clean. So the cost and complexity of electronic circuits. If you're not capable of operating at high voltage distortion, when there's high voltage distortion, the operation can be a problem. If it is expensive to make, cost of ownership can be high. So the harmonics inside the plant will remain. So this is an important thing. So normally these active filters closer to loads in smaller quantities or smaller sizes can become very, very expensive. So normally what they do is to get rid of harmonics and to avoid penalty by the utility, they straight away install it at MB panel. So the harmonics is reduced at the measuring point, PCC. So there is no issue, don't pay a penalty. But what happens is you are sick, you're not taking the medicine, you are giving it to somebody else. So you don't clean up your harmonics inside your plant, and you are paying so much to reduce harmonics. So the harmonics inside the plant will be still circulating and circulating in other nodes and causing all these problems. So really not followed a good technique or good electrical practice. So that's an important point of this active filter. There are 2 points. One, it is very expensive, difficult to maintain, cost of ownership is high. The harmonics inside the plant will remain. This is a key issue. So in an advanced universal harmonic, the price is less. You can install it closer to load. So reduction of low frequency up to the 50th. So it performs much better than the active filter because it reduces harmonic up to the 50th. So sometimes you can have other harmonics also. 25th, 27th. It's possible in some issues. So up to the 50th, it can, and it doesn't introduce any high frequency harmonics. So you can improve the performance of the harmonics by improvising and adding some winding to filter much better. So we can reduce. If we have that less than 5% also, we can decide. So the terminator design protects against power system resonance. So the capacitor installed in the filter is very small. So it doesn't even at low loads. There is no overcapacitance and consequently no resonance also. It treats all the characteristics of low harmonic generated by 3-phase guide bridge rectifier, 5th, 7th, 7th, 13th, all the harmonics. It mitigates harmonic closer to loads, improves power factor, protects and extends the life of the equipment. So if it is connected to a drive, the drive, breakdowns can be very less, very infrequent, or it will not cause any breakdowns at all. It will protect the drive. The drives can fail for some other reason, but it will not fail due to poor power quality. It's capable of operating in voltage distortion environment up to 8% without deviating. So even if there's voltage distortion at the input, it can still operate comfortably. It is the only problem for this. It can be heavy, it can be a little larger. So you need to find space to keep them. This passive filters are installed closer to load, hence many passive filters will be required. So you may require a number of passive filters for different non-linear loads. So you will have to use your judgment to see that you keep to the minimum. So this is I've spoken from 5th harmonic to the other harmonics. So this 3rd harmonics is a serious issue in many places, especially residential areas or computer data centers and all that. Where you install with UPS, single phase UPS or single phase lighting loads, LED lighting loads, single phase UPS computers. All this have caused 3rd harmonic, heavy 3rd harmonic. So if you see this diagram, you see this pulses, 3rd harmonic pulses. They are all, if you see, and they add up to the neutral. So the neutral current increases, and they flow to the neutral, and then it circulates in the delta of the distribution transformer. So the current, 3rd harmonic's magnitude is more. It can cause a lot of heating because there is no enough path or grounding wire, ground them also. So they circulate inside the delta of the transformer. If you see this thing, the other normally the other phases A, B, C, R, Y, P, A, B, C phases, they are at 120 degree phase shift. So at the neutral it will be 0. So vector sum will be only 0. But if you take third harmonic, they add up. You can see this. They add up in the neutral. And so now they can be 3x. So like I told you, if it's a industrial plant, 100 amps in each phase, there will be 300 amps in the neutral. That is a very dangerous situation. Normally, you have 4-wire cables only. Sometimes you have 3.5 also. So you'll have to double the neutral and all that. In spite of that, heating, you cannot eliminate neutral without eliminating this third harmonic. So this third harmonic is a serious problem in many installations, especially in single phase where the loads are single phase, residential areas or data centers. Sometimes then they can be a serious problem. So if you take again, this is again to explain how these neutral currents flow through this neutral harmonic eliminator, and then they flow through the winding, and then they go back to the load. And they get cancelled because what we do is because of the windings of it's bound in such a way, we call it zigzag winding. The third harmonic is phase shifted by 180 degrees. So all the third harmonic is phase shifted. So once they are at 180 degrees, they cancel out. So once they cancel out, the phase wires are offloaded of the neutral wire, neutral thing. The third harmonic current or different harmonic, and the neutral also is offloaded. So all there's so less heating in cables and all that. So waveforms neutral is designed to treat triple N harmonics. Triple harmonics distort voltages and currents. So they distort voltage and current much more than other harmonics, and connected in parallel. See, the important thing of this filter is that they are connected in parallel. So the sizing can be relatively smaller than the entire, it need not be sized to the entire load requirement. As much as the neutral currents are there, it is sufficient to take care of. Sometimes the neutral currents can be, say, 20% or 10% of the load. So you can design it to just to 10% of the neutral current to take care of the neutral current, to improve it. So it is connected in parallel. So connection also is a very simple exercise. And connected in parallel on the power distribution or load, the low zero sequence impedance of the neutral harmonic elevator will attract the zero sequence harmonic current and provide alternate path back to loads. So it provides an alternate path back to the loads. So neutral is offloaded also. This offloads the neutral conductor and upstream transformer of the harmful current that cause waveform distortion and thermal stress. I just explain this in residential places especially. You have loads that have third harmonic. You just take your washing machine, which is a drive-driven machine. You have a single phase drive, which will have third harmonic. A lot of it. In fact, I've tested a washing machine, and I found that 40% of third harmonic, 20 to 30% of third harmonic current is. And LEDs, some LEDs are very poor drivers, so they can generate a lot of harmonic, third harmonic. So similarly, you have other SMPS, your computer, your music system, and so many other equipment that have only single phase and power supply. And besides that, you can have imbalance in your residential places. So in all this, you can improvise this design to design it in such a way that you can install it along with the distribution transformer. To install this, you can offload this neutral current. You can prevent the failure, of the bigger transformer. So most of the residential places, you will find that transformers, humming sound is there, the heat is there, temperature is there, because it happens all the time in the evening or during the night, because the residential places, all the lights come off and they use the TV, they use the music system, they use computer. All this adds. Sometimes everything can be in a single phase also, and then there can be imbalanced. So you are creating a dangerous situation. So this is how it works. So if you have from the neutral, from the load, all the neutral current flows into the winding, in this way, and then you have from the power line, you get the third harmonics in this direction, and the third harmonics they are 180-degree phase shifted, so they cancel out. So the phase gets offloaded, and also the neutral wire also gets offloaded. So you will not have any current flowing into the delta of the distribution transformer, heating the transformer, or one particular winding, heating up and causing failure. So this is a it is used in a lot of countries, like in Europe and US. I wonder why we are not using this innovative design, innovative practice to reduce harmonics. It can be a very useful. Probably your energy management cell can suggest to the board to use these transformers and save the transformers. It can reduce the cost substantially. It is very useful in computer centers, where you have a single phase load. This type of filter will be, can reduce harmonics. Because even if they have a UPS, UPS being a low high impedance, the voltage waveform can get distorted, and the ride through facility can reduce substantially if you have that. So you can introduce between the UPS and the thing. You can use this filter in, you can use the double winding type of zero impedance transformer or auto transformer. So both ways you can reduce the third harmonics circulating in the computer center, because the third harmonics will, if it is not filtered, will circulate inside the computer, inside the UPF. It can increase the temperature. So about 23% you can reduce the heat inside it. So air conditioning will work lesser also. So you can improve efficiency of data center also substantially. And then this is a very good thing for medical center, for medical centers, for testing labs, instruments, very expensive instruments for that. This type of filter will be very useful in spite of having a UPS, because the voltage can still get distorted when you have current third harmonic current. So this is Waveforms Advanced Harmonic Mitigation Transformer. So this is, I already told you, you have when you have a drive with 6 pulse diode, we have a transformer called Y11. Okay? So that is a 30-degree phase shift. So when they have the one output is 30-degree phase shift, the other one is a 0-degree zigzag transformer, which is called a zero sequence impedance transformer also. So you'll find when you have connect two loads like this, you'll find 3, 5, 7, 9 all eliminated. The third harmonic gets eliminated in the zero sequence winding, and the fifth, seventh they get cancelled out in the bus bar. So the fifth and seventh will still flow from here, and when they flow in the opposite direction, they get and when it is at 180-degree phase shift, they cancel out automatically. So you can use for data centers with 2 outputs for computers and all that. So in some places in multi-story building, where you have data centers or instruments or things that you need to high degree of protection, this transformer will be a little expensive. The only problem issue is it may not be that effective. It will be only a 60 to 70% effective filtering, and the imbalance will also cause some problems. So and it is very expensive and costly because it needs more space, and all this disadvantage will be there. But it will reduce the the I2R losses, the eddy current losses, all this will be mitigated, and it will improve the reliability of the equipment connected to it. So this is for a UPS where we installed isolation transformer with a zigzag output, isolated, and also with a zero sequence impedance transformer, or neutral with a neutral compensator. It's also called a neutral compensator. If you see that the loads the 20 kV UPS, right, so loads were less. There were 10 amps and 8 amps and all that. But you see the harmonic current, third harmonic current, you will find that it is very high at 65% almost. And the maximum harmonic current was very high. Third harmonic was very high. And but after we installed this isolation transformer, we found that the load was balanced, current was reduced, and if you see the neutral current, it's coming down to 5%. So excellent performance by the this type of transformer. So it is very ideal for for instead of using K-rated isolation transformer. K-rated is nothing but you have K9, K13 and all, which means that it has to withstand 9 times the temperature rise. So you have to wind it in such a way that it withstand the thing. They use multiple windings and double neutral and all that in the K-rated. It becomes expensive and becomes secure, expensive. But it does not mitigate. But even after spending that much, you don't filter the harmonics. You don't filter the harmonics. The harmonics will remain. Only thing you get an isolation function. So the earth neutral voltage you can reduce. That's all. But or bring it to zero. But you don't really reduce the harmonics. Energy saving also is not there. You don't reduce the temperature in the UPS or in the computers. So it's very simple. You can use this zero impedance transformer, neutral compensator, neutral eliminator, whatever name we call it. It's a very useful device for residential, especially in a multi-storied residential location. But sometimes the neutral current can go very high, and you have transformer failure. I think if you take an account of the transformers that fail, the main failure is because of third harmonics, the neutral current harmonics in most of the transformers. The issue is that. So if you solve this problem, you can save a lot of transformers in any state. The HMT is some applications of the session. So I come to the last part of the sine wave. This has nothing to do with the input harmonics that is fed into the source. This is basically, I think, for energy management cell, it will be very important because I am sure you would have seen drives in one place and motors away for 2,000 meters away or 1,000 meters away or 500 meters away. So what happens is the output of any drive is a square pulsed waveform. So because of this IGBT switching, which we may switch from 2 kilohertz to 8 kilohertz. So this thing, when routed through a cable and long distance cable, they have a capacitance effect, and the motor will have a reflective wave because of this winding. It generates a reflective wave. So they interact and they cause a high DVD-DC pulses. So this DVD-DC pulses can be 2x or 3x. It depends on the severity of the pulses. So when motors are connected through long cables, the high DVD pulses generated by PWM inverter cause reflective wave on the cable due to impedance discontinuity at the motor terminal. The voltage transition can be twice of the inverter output. It can be much more also. So due to DC electrical losses and cable resistance, damp ringing occurs. So this ringing is a very dangerous thing. You can see this ringing here. It causes a transient, and then the ringing also occurs. So the frequency can be in the order of 50 Hz to 2 megahertz. This type of cable between motor and drive system grounding play an important role in this phenomenon. So it can cause a common mode noise, and that it can go back to the drive, and this works it can interact with the capacitor being a low impedance path, and then it can cause tripping or failures also. So productivity also can suffer. Then the insulation also can suffer, as you can see, the puncturing of the insulation. By inserting a sine wave filter between the drive and the motor, we can dramatically improve the performance of the drive and the motor. So there are many cases where people are not still aware that the output of the drive is not a square wave, it is a square wave and not a sine wave. So the sine wave filter converts this square wave into a sine wave. So that is the other thing. It is basically an LC filter, and it's basically a LC filter, which will convert this high frequency square wave pulse into a sine wave. So thereby it eliminates all the transients that are generated by the long distance cable and the motor itself. So this is a 1450 ampere thing which we installed for multiple drives, driving a single motor of 900 kilowatts. We have installed this 1450 LC filter, or we call it sine wave filter, and they were having issues like motor burning and all that, failures and all that. So once they installed it, they were quite satisfied with. They placed for the second one. This is done at IOC and RDR project. They have ordered for the second one now. So we are going to install this filter again. So they are quite satisfied with the performance of this filter. It's a very useful filter for protecting the motor. Motors are very expensive, and plus, there are places like pumping oil or water and all that. In such places, failures can be very disruptive. Can cause a lot of problems. So it becomes important because of that to prevent failure. So it has the highest level of filtering. The voltage THC is normally 30%, and all it is reduced to 5%. Then the voltage drop is also avoided because we have a capacitor added to it. It's a smaller capacitor. And it has a high efficiency. Then the carrier frequency range of it can tolerate 1 to 15 hertz, kilohertz. So it filters out the switching frequency current of IGBT. And it's a reliable and proven performance because they are total magnetic. So the capacitors also can last you 1 lakh to 2 lakh hours. There's no issue with it. And we can protect about it and protect the motor. So this is some of the installation. So this is how we test our thing, short circuit test, high voltage test, all this thing done. So this is one filter which we took the measurements online. So you can see from as we keep loading, the harmonics and then reduces to 9.5% to 8%, 5.44, 40 to 45%. We are bringing down to this level. So this was tested in real time.
No, sir. Actually, we are running out of time. We have 10 more minutes.
Yeah, we have to. I'm through it. I'm through now.
Okay.
We can go to the question and answers question. I'm sorry that.
No issues. I just wanted to give a ringing bell.
No. I was watching my clock also. I thought I will just finish it. Because I've been doing this repeatedly, so it is approximately this time.
Yes. It was a very interesting session. That's what I was hearing from the initial.
Yeah, but there will always be a lot of questions to be asked on this, and we are always open. But anytime you can, drop a mail.
Actually, what happened is we have one more meeting which is running through, which is concerned to the government. One meeting was called on suddenly, all of a sudden. So some members couldn't join, but I will share this PPT and the videos with them. So some of my colleagues also participated in this session. Mr. Ijaz is looking after demand side management and mandatory energy audit. He is looking after. So he is also there. He has also asked a couple of questions. Then Mr. Sharath is looking after this patch scheme, reform, achieve and trade, and the environment of energy auditors and industries he is looking after. So myself, I am looking into the utilities, then water pumping stations, then MSMEs. So these are the portfolios I am interested in. So we had some more portfolios they couldn't join. So I will start reading the first question. So Srijaz has asked, is it possible to identify the harmonics from the performance or operation of any equipment?
Normally heating is one thing. Abnormal heating can indicate there is harmonics. Then if there is third harmonics, you will find that neutral wire heating and sometimes burning at the edges. Because what happens is harmonics tend to flow to at the top of the cable, because that forms the low impedance path for the harmonics, high frequency harmonics. While the 50 hertz flow through the core These harmonics flow through the thing. So that skin effect, you'll have harmonics, going between the load and the source. So they'll be colliding. The electrons may be colliding, and then they cause temperature heat. But another simple method is measuring the peak current. If you have a good multimeter, the peak current and the RMS current. If the peak current is 2 to 3 times, then it means 2:1. If it is 3 times, the RMS current is 3. That's a simple way of measuring the harmonic current, other than using the power analyzer. So that's one way of simple. Then you can measure the earth neutral voltages. If the voltage between earth and neutral is high, and neutral current is high, you can figure out that the issue is one of harmonics.
Okay, sir. Okay, thank you, sir. So there's one more question. That question I already posted. We have heard some factors like apart from PhD, TDD, and these harmonic things. We have heard some factors like IT product and KT product, which with respect to this is IT product and KT product with respect to the radio interference. This is the electromagnetic interference caused by harmonics.
See, harmonics can also cause EMI, electromagnetic interference and all that.
So that is measured using IT product and KT product. Is there any?
This is a low harmonic, for low side harmonic, 250 But higher frequencies, is not the subject that I had covered. That's a different subject. It can be these harmonic, these noises and all can be introduced by all the equipment, SMPS, drive. It can be radiated and conducted also. So it can be both ways. So that's a different subject altogether. They do.
That's it. I wanted to know whether any instrument is available to measure
it is available. Spectrum analyzers are available, and then they have with antennas and all that. So when it is radiated,
actually, Simon sir, we are having two numbers of Fluke 435. So in that power analyzer, and most of the power analyzer which I have shown, because for energy audit we usually use this power analyzer. Some of our energy auditors, they are having Cricard, some people they are having Megger. So we are using Fluke from a very long time. Two numbers we are having. So in that also, these analyzers, we don't have this IT product and KT product. That option is not there.
It is not there. No, that's a different subject. No, it is a higher frequency. No, it's a very high frequency. In kilowatts and megahertz. So these are only for low frequency, up to 50th. You can measure only up to 50th. The others you'll have to use the spectrum analyzer and the special antennas and all for radiated. It can be radiated and conducted. No, high frequencies can be. Mostly, if you eliminate these harmonics, you will avoid this other harmonic, this EMI interference also. So this is the basic to that also. So this is the operating cost. Typically, if you see, once you install, there's a lot of substantial. The return on investment can be as low as 18 months. So within 18 months, you can recover by savings. There's a lot of work. I appreciate that energy management cells have been very proactive and agile in responding to.
Because that's what the energy audit. What we do is this power quality is a part of the energy audit. The energy audit what we are doing. We have around 49 embedded energy auditors. So the energy audit these people they are doing, the power quality is a part of that. So these auditors will be using power analyzers and they will be suggesting whatever the mitigation techniques. So it is up to the customer that he follows that. He will suggest them. The customer he has to invest and he has to get the return, as you said.
Yeah, there's a slight difference. So improving power quality will definitely improve energy efficiency and other problems, failures and all that. But what is important is this high frequency can cause a lot of problems inside a plant. You can your productivity can increase substantially. Most industries are losing a lot. The awareness about power quality seems to be poor in the country, and a lot of people don't have an idea. They straight away when they have a power quality issue, and in Tamil Nadu when utilities started. When the EV started,
Tamil Nadu, the penalties, I know. Harmonic penalties. In Kerala, it is not imposed.
Yeah, most of them didn't use the right technique. They straight away went in for active filter, installed it at MV panel. And after some time, there were a lot of failures of the 6th panel. They found it difficult.
Kerala, we have power factor penalty range is enhanced to 0.95. Before 2-3 years back, it was 0.9. Now the minimum cutoff range is 0.95. Below that,
yeah, 95. But you know, the ideal way, instead of having penalty based on this IE 519 and all, you just go and say, okay, we want to charge you with KVA. If you charge KVA, if you have harmonics and all this, the KVA will rise. So everybody will be bothered about paying more on KVA. So they will try to be efficient. That's what instead of, you know, many states have adopted KVA, not kilowatt. So many states, you know, Telangana, Andhra, Uttar Pradesh, Gujarat.
Here also, so here also for HT consumers, for LT consumers we bill on kWh. For HT consumers we have a two-part tariff. We bill on both on kV and kWh. Both are.
Yeah, that you do it on MD, no, maximum demand.
Yeah, MD, yes.
In other states, it's not even MD, straight away KVA for everything total.
Okay.
So in that way,
fine.
in that way, board is also recovering, and people, all industries will be forced to, you know, implement energy efficiency measures. So this is the way you can do it. You know, KVA is very simple. You know, this measuring harmonics. You know, you'll have to send an engineer measure the harmonics, or you have to connect
and
it.
One more thing. When you told this, I remembered one thing. When we asked on brand, I don't mention the brand. That brand is very renowned with its power analyzer. So they tell that this harmonics is not causing energy loss. The harmonics is causing. It is not accounting to the kWh, and it will account to the KVA. So
but this is again a myth. Now, what happens when you have a harmonic? The current flowing through the impedances or to the cables or other impedances. What happens is when you have multiple harmonics, they are colliding, electrons are colliding. What happening is you lose by heat dissipation. It dissipates as heat. So the measurement is not there. You can't. There's no measurement for heat and converting it into kilowatt. So this losses are there. It doesn't mean you're not losing. You're losing. So that is again temporary.
Harmonic current is it reactive current or active current?
This reactive current goes off as heat temperature. Whereas power factor you see it as a kilowatt or kVA. But in harmonics, what happens is there are so many harmonics, and I told you, the Ohm's law applies for each harmonics. So there's losses in each harmonic. These harmonics are lost by heat, temperature, and heating of cables, transformers. All this is not measured in kilowatt.
In some power analyzers, we have seen one option called energy lost. The harmonic analyzer will directly give you the energy loss. But some other brands tell that this energy it cannot be taken as energy loss because it is not related to kWh.
Yeah. What they do is you have to feed in the particular information about cables and all that. It does some K rating calculations, and then it figures out what is the kilowatt losses.
Okay. Thank you, sir.
So the temperature rise is a serious temperature rise in motors. If it's the negative sequence harmonics, what happens is reverses the magnetic flux. So what happens is the motor rise.
We have seen the vibration.
Vibration will be more. Noise will be more. All these losses cannot, it can't be reflected in kilowatt sometimes.
Okay. So, participants, any other questions? I think only Ijaz is there, Ijaz and Sharat. So, do you have any questions, any further questions, so that we can address whichever we have seen in our project? Any feedback from energy auditors? So there is one question regarding that this generators, this DG sets, normally this manufacturer, they tell that we should operate at 0.8 power factor. But in some sites we have tried improving the power factor, and there is no harm to the generator. Even this one, keeping in the mind that suppose it is a 500 kVA generator. So this is designed with an alternator having to deliver 400 kilowatts.
You can improve the generator manufacturer. So the generator manufacturer, what happens is they tell you to switch off the capacitor because they fear the overcapacitance will cause problems. But no, generators can operate at point. I have a special write-up on that. I can send it to you. You can operate up to 99 also. 9. There's no overcapacity.
Okay, there's no issue. Okay.
Yeah, you
Because
should
some
not
one of our projects we have operated. That's it.
yeah, because they tell you to operate at 0.8 because if there is a harmonic load or harmonic current, what happens overcapacitance can cause resonance. So to avoid that, they will say, okay, don't operate with thing or operate within 0.8, so that this resonance is avoided. So it's simply told, but it can operate up to power factor 1. No, you should not have overcapacitance and cause resonance. That's the only issue.
Okay, when the capacitance is increased, it will affect the AVR, right? The exciter.
Yeah. It can cause resonance. No? It can interact with overcapacitance, can interact with some loads, and with the network and cause resonance. And at that time, generator can be an issue. That's why they try to keep it within 0.8. But if you have a good power quality thing mitigated, or if you have a system network which is mitigated of harmonics and less than 6, 7, 8%, you should not have a problem. You can operate at point. You can improve your efficiency, but by operating at 0.8, you are losing a lot of power also. No? Maybe it's more.
Yes.
So that's not the right way. So if you mitigate harmonics,
and also one more problem is that in our systems we have APFC panels. So these APFC panels, there will be an APFC relay which will sense the reactive power demand and it will switch on the capacitors accordingly. So how it will sense is like that. We have placed the CT. A CT will be given to one phase of the system. So usually this we place the CT in the transformer secondary. So that when DG is on line, the transformer is suppose there is a power failure. The transformer will be off and the DG will be switched on. So this time we will not get the correction. This FAC will not function. So we have to switch on to the manual mode either.
Yes. Yeah. See, nowadays you have an APFC panel that you can sense the generator also both.
And how can that be done?
I think they use 2 CTs for both the generator and or a common.
Okay. The relay is having such provision.
It will automatically choose the generator, and it can operate.
Okay, just the relay may be having that function, right, sir? The APFC relay.
But sometimes the APFC relay itself, if you have harmonics, there will be this phenomena called notching, where sometimes the voltage can for a moment fall to 0 in few seconds. At that time, there's an erratic digital signal and it can malfunction. Many of the cases where there is harmonics, these APFC panels don't work at all.
Okay.
If there is harmonic presence, the working of the digital APFC itself, relay itself could be a problem. And then this APFC switching also can cause a lot of surge current also. That's why they have this anti-resonant filter which can mitigate that thing. Sometimes you have thyristor switches which will switch at zero current.
Yeah,
so you will not,
thyristor switches. Okay.
Thyristor switches. So all these are other techniques where you can mitigate surge currents. Capacitor switching is a very dangerous operation. Especially that is why you should have capacitors from different ranges, so that you don't have one 50 kVA switching simultaneously and all that. So designing the power factor panel is also very critical to have a good power quality. If you have a thyristor switch, nothing like it. Or with anti-resonance.
But sir, some we have recommended thyristor switches somewhere, but these thyristor switches are very costly compared to these contactors.
Yeah, it is expensive, and then it does cause failure. If temperature rise and all that, it can cause of
it is almost 7 to 8 times the cost of the.
It is very expensive. It is very expensive. But where you have a rapidly changing loads, you require this thyristor.
That's what. In arc furnaces.
But what happens? You don't solve the problem with thyristor switches. Suppose there is harmonics in a welding load. These thyristor switches will not work at all sometimes. The erratic signals will be the firing circuits, especially is sensitive to harmonics. Firing circuits can play, faulty firing circuits can cause a lot of problems.
Okay.
So harmonics ratio is a problem in thyristor. You need to filter harmonics. The welding loads is a very difficult load to handle. So improve power factor and all that. You have to reduce harmonics also, because normally you have thyristor switches in welding loads, and so the
Sir, in Kerala, Kerala, who are your prominent customers? You are having customers?
No, I don't have any customers there. So Chennai only.
Okay, okay.
But we are,
So it'll be,
these products are come lately only, just 1 or 2 years old only. We have got only about 15,
because
20
in Kerala, why we are asked is lot of new buildings are coming, including the malls, then multi-specialty hospitals, then flats are coming up, then IT parks are coming up. So in the coming 2-3 years, there will be a boom of large high-rise buildings.
Yeah, in one residential issue, I think in Kochi, that issue came to me. They are having this power factor problems, no failures of capacitor. And then I saw that they are having a lot of trips with drives and then single phase loads. All this is causing they are not able to maintain power factor. They are working penalized. So they were asking for a solution. So I suggested that you have to mitigate harmonics. There's no other choice. So these issues are there, especially the single phase loads in areas. Your transformer failure can be, you are overrating a transformer normally. If the load is say 200 kVA, your 1000 kVA they use. Just to because one single phase gets loaded, it has to withstand. But if you use something like the 0.6 and 50 transformer, you can reduce the size of the transformer, and then you can prevent failures, and then a lot of savings can be there. It's a very revolutionary product. I don't know why this country is not thought about it. Probably this energy management cell can take it up with your.
Yeah, we will take it up. Yeah, that's what we have brought some light to this.
I will send you some more literature on this about how transformer and the grounding transformer can be very effective. Zigzag transformer.
Okay, the generator issue also you can send. You have some article on generator.
I will send.
And one more thing, I just saw from your slides that you are doing some analysis on ETAP software. So we have been using it long before. So in that, to analyze harmonics, we have seen like in some loads they have given, there are some standard loads in ETAP. So in that loads, we have two options, either IEEE 519 equation, or we have to model. So which procedure you are using? You are using the standard procedure, or?
See, we have got another software called Solve. Okay, that's solver we can feed this information about the non-linear loads and other loads, and see how much that is much more accurate than ETAP. So that will tell you exactly.
We will just get a standard idea, right? They have a standard equation.
ETAP will give you an idea about the harmonic loads and what to be done and all that. But this is
what is the name of the other software? Solve.
It is called Solve. It is a software by an Canadian company who are manufacturing this universal passive harmonic filter like myself. In fact,
it is a paid software, right?
Yeah.
It is a paid software, right?
Okay. It is a free software only. Okay. You have to register and get it. But we do have it.
Can you spell it? It is Solve. SOLV.
SOLV. It's by Myris International. Myris International. You can, simulate and tell you, okay, this is the load, what.
This is only for harmonics. It's dedicatedly for
harmonics.
Only
dedicated for harmonics. It will tell you what is the what will be the losses in the transformers, and what will be the power factor will improve, what harmonics will be. It will tell you the kVA, kilowatt, power factor, everything it will tell you. So suppose you give me a input SLD with all these harmonic details, I can put this and tell you, okay, you solve it like this. This is the ideal way of improving the voltage and the current waveform. Ultimately, it's about having a sinusoidal wave voltage and current waveform. That's it.
Okay, sir, we are shooting out of time, so I think there is no questions from the participants.
Okay,
it is we are nearing the lunch time. So anyhow, it was a very informative session and very useful, because you have taken a lot of time to present these concepts of power quality. Even though we were doing energy audits and power quality is part of that. We were not much deeper into this type of this. So in future we will think much deeper like this, because it can give good savings. So yeah, we will be continuously associating with you. So thanks for doing that session.
Anish,
So that's all from my side.
Yeah. Anish, you can bring about yourself can bring about a revolutionary change and in saving for industries and for the state itself. If you start employing these techniques for industries and for for the electricity board also, you can save substantially. The savings can be in millions actually. So can you imagine if every industry saves say 10%, 10%. Just see the kilowatt used and how much you can save and how competitive industries can be. The problem of industries is we are not competitive. We can be competitive. Thank you. I appreciate your proactivity and agility in accepting our invitation. Thank you very much.
Yes, sir. We will ask for your service one more time when there is any program planned. This was not well planned.